Okay, polyprotic acids and gas formation reactions. And for polyprotic acid, so that's any with two or more H pluses in the front here, the acidic hydrogens that can react with a base. Now, if we have HCl, I'll just do an example here, plus sodium hydroxide, that's a neutralization reaction. And what we get is NaCl, we get the salt, and we get water. But if we have a triprotic acid, this is polyprotic, there's 3 H pluses, and that's what they're asking us to do. Well, we need 3 sodium hydroxides to react all of the H plus that's available. We have 1 here, so we just need 1 sodium hydroxide, but when we have 3 H pluses that will be coming off of this species, we're going to need 3 sodium hydroxide, so we'd end up with Na3PO3 and 3 waters. Each H plus would react with an OH minus, and we'd be done here. That would be it. Now, we can do it all in one go, but they're asking us to do it in successive neutralizations. So we have, we start out with H3, so let me just, it's a different thing here. So we can do it in 3 steps rather than all 3 at the same time. So if we have 1 sodium hydroxide, one of the H pluses will come off. We'll have sodium dihydrogen phosphite now. Phosphorus acid changes to this salt. And then we have water. Now, even though there's a sodium here, we still have 2 hydrogens left, so that sodium dihydrogen phosphite can react with another sodium hydroxide, and another H plus will be removed. Now we have Na2HPO3, so this would be sodium hydrogen phosphite, or monohydrogen phosphite. But there's still a hydrogen here, so we do the 3rd step. Get this all in here, plus the sodium hydroxide. And that removes the last of the acidic hydrogens, the last of the hydrogens that are available here. So we have Na3PO3 plus H2O. Now, what I'm saying is, well, forget about the top one here, just this reaction here is equivalent to these 3. And the way to show that is if we add up these equations, cancel what's on what's the same on both sides, we'd end up with this equation. So we have, I'm going to try to write it all out here. So add them up as if you're adding up equations, mathematical equations. I'm going to leave off the aqueous just to have room here. But no, there's aqueous for each of these. Then we have 3 sodium hydroxides. Then we have NaH2PO3 plus Na2HPO3 plus Na3PO3, and I'm going to have to bring the waters down here. But they're products as well. And you can see that the sodium dihydrogen phosphite cancels, sodium monohydrogen phosphite cancels, and we're left with phosphorus acid plus 3 sodium hydroxide goes to sodium phosphite and 3 waters, which is what we had up here. So when you're asked to do the successive neutralizations, it does take place in these steps, one at a time. But of course they happen very quickly. So saying that this is what happens is fine. But if you do that without doing its successive steps, you miss some really important species that develop through the reaction. Even though they're canceled out as we go, it's nice to be able to see them. So whatever you're given, this is triprotic. You'd be given diprotic like sulfuric acid, which will just be two of these, only 2 reactions. But you know, whatever you're given in the way of a polyprotic acid, you should be able to break it up into the steps. Okay, now what do we have here? Complete the following gas formation reactions and write the net ionic equations for each. All right, now for me, I'm only interested in you knowing that when you have an acid and a salt that contains a carbonate ion, that's going to produce CO2 as a gas. That's what happens anytime you have a carbonate reacting with an acid. Now, what students will do if they have to complete a reaction, they know enough to do this kind of switching of partners. The sodium goes with the bromide, the hydrogen with the carbonate, and what they'll do is they'll have, and you can see that it's going to be, you can balance it later if you don't see it, but it would be 1 to 2 here. You get 2 sodium bromides, and then they have H2CO3. Now, this is where a lot of students will stop because they won't realize they're dealing with an acid and a carbonate. This is the only time it happens for us. There's 2 other types of gas formation reactions. I'm not interested in those. If your instructor is, if someone else is teaching this course, you better check with them. But for me, it's enough for, as long as the students can recognize the carbonates and the acid, because those are the ones that come up the most. The reason I don't deal with the other gas formation reactions is because the gases that are produced are generally dangerous. Or not generally, they are dangerous. So we don't often do them in the lab. But carbonates and acids, that comes up quite a bit. Now, CO2 gas is produced. So what happens is this guy goes on to produce water and CO2. It breaks up. It's carbonic acid. It breaks up. It's unstable and breaks up into water and CO2. So the real reaction that you want to write, and then I want the net ionic equation, right? Yeah. So I'm going to rewrite it. You'd balance it this way on this side, and then on the other side you have your 2NaBr, and then you can certainly do this step, but you'd have to finish up in this form. Has to be this. To show that, yes, there's some carbonic acid that's left over, there's some hydrogen carbonate ion that's left over, but the vast majority of any carbonic acid that is produced is going to turn into CO2 and water. So now the net ionic equation, well, I'm gonna skip the phases for now because the final form, this is the complete ionic equation, but that's not where we're stopping. So do it very quick, but here we have water. That one I had to put the phase because it's not aqueous. And this is a gas. So see the sodiums are spectator ions, so are the bromides. So we have CO2 2-. This is the net ionic equation. So anytime you finish up, if I want the complete ionic equation, you should put the phases in. If I just say the net ionic equation, you can make your way down, but once you're done, once you have the final form, you have to put those phases in. So this stuff up here is kind of just setting up the problem, getting to the final form, but the final form has to have the phases when we're dealing with this kind of problem. Okay, here's another one. We have sulfuric acid, and we have a carbonate, potassium carbonate rather than sodium carbonate. So you know that CO2 and water are going to be 2 of your products. Now, sometimes it's hard for students to see how to go directly into CO2 and water. What I would recommend is, yeah, you can certainly do this switcheroo, you know, switching the partners, and make sure that we have everything that we need here. Yeah, it's 2 and 2, so that's good. So then come down here and write out since I only want the net ionic equation, you don't have to worry about the molecular. You just complete it so that you can figure out what's going on. Sulfate. And I'm putting in the phases just out of habit, but you certainly don't need to do that on this step just because we're trying to get to the end, to the net ionic equation. And the carbonic acid breaks up into these 2 products. So then we see the potassium cancels, the sulfate cancel, and we're left with. It's different than the first one because it's a diprotic acid, but it's still strong. So we end up with this simple form. If this is a weak acid, let's say like H2SO3, then we'd have to leave it intact. This would be H2SO3 here, which would get carried through. We'd have to. Actually, let's do one of those out just to see. Okay, so let's do out sodium carbonate and HCN. Since this is a weak acid, just to show you what I'm talking about here, so we have, it's going to be 2. And then this is aqueous, and this is going to break up into 2NaCN aqueous, and I'm just going to go straight to it. It's two H pluses and the CO3 2 minus can produce water and CO2 gas. Now the difference here is that when you break it up into the ions, so we'll do the complete ionic equation but without the phases, this stays intact because it's a weak acid. This time it stays intact. The strong acids break up, 2N, so just to show the difference that you're going to see. And this would be liquid and gas just to differentiate. And then, so these cancel. The only spectator ions this time were the sodiums, so we have CO3 2 minus. Yeah, and this is what I stopped because I knew on that last problem just kind of doing it quickly without writing it down was a bad idea. So now we can see that when we have a weak acid, there is a bit of a difference. Before this was just 2 H pluses, now we have this counter ion that's attached, so it's going to look slightly different. So just be careful.